All right, so that leaves us with y equals 1 over pi squared plus 1, and if we distribute that one, plus 2 over pi x minus 2 over pi. So that leaves us with y equals 2 over pi x. 2 over pi minus, well, that should be 2 over pi squared. There you go. 2 over pi squared, negative 2 over pi squared, plus 1 over pi squared is minus 1 over pi squared plus 1. You actually don't have to combine the 1 with anything, since technically that would just be your plus b there. All right, so any questions on that one? Okay, so it's really kind of the same thing we've been doing before, but this time with parametric equations. Little twist to the formulas, that's about it. Okay, so now we're going to look at the second derivative of a parametric function. Which looks a little bit different than the second derivative you're used to. Oh, anyone's still writing? All right. Second derivative of parametric functions. Okay, so we already know that dy dx is equal to dy dt over dx dt, or y prime of t over x prime of t, where dx dt won't equal 0. Okay, so if you have the derivative with respect to x of y, then we can have the derivative with respect to t. Just bring that y out to the front. Derivative of y with respect to t over dx dt. So what we're going to do here is we're going to replace y with dy dx. Uh-oh. Okay, so that gives us the derivative with respect to x, dy dx equals, the derivative with respect to t, dy dx over dx dt. Which gives us the second derivative of y with respect to x equals the derivative with respect to t of dy dx. Because we know our dy dx is just going to be a function of t over dx dt. And that's how you get your second derivative for a parametric function. Yes.
So we only derive y the second time, we don't derive dx the second time?
Well, when you get your dy dx, remember that's y prime of t over x prime of t. So it would still be a function of t.
Okay.
So you're just getting that function again by t. All right. You can leave that up there for a little bit. All right. Okay, so for our first example, calculate the second derivative for the plane curve defined by x of t equals t squared minus 1 and y of t equals t to the third minus t plus 4 at the point t equals 6. Yeah, that might work. Okay, so the first thing you have to do is find your dy dx. Okay, so we know our dy dx is y prime of t over x prime of t. Oops, clean that up just a bit. Okay, so our y prime of t is 3t squared minus 1. And our x prime of t is 2t. Okay, so we have our dy dx. Okay, now next we just have to find our second derivative. Okay, so we know that our second derivative formula for parametric is derivative with respect to t of your dy dx over dx dt. Okay, which means we're going to have the derivative of your dy dx, which is 3t squared minus 1 over 2t divided by dx dt. Okay, so all we have to do here is the quotient rule. Move that over just a little bit. Okay, so you have your denominator times the derivative of your numerator, which is 6t, minus your numerator times the derivative of your denominator all over your denominator squared. So 2t squared, and that's divided by your dx dt, which is, where is it, 2t. Oops. Okay, so this will simplify to become 12t squared minus, that would be 6t squared minus 2, so that would be minus 6t squared plus 2. 2t squared, that becomes 2t to the third, so 8t to the third. And we can go ahead and combine those two like terms there. So you have 6t squared plus 2 divided by 8t to the third. Okay, so that's your second derivative. Okay, so now we just have to find it at t equals 6. You have 6 times 6 squared plus 2 divided by 8 times 6 to the third, which becomes 218 over 1,728, which simplifies to become 109 over 864. Any questions on that one? All right, leave that up for a few seconds. All right. Okay, so let's say if we want to calculate the second derivative for a parametric graph, well, not graph, but function, parametric curve. Defined by x of t is equal to square root of t, and y of t is equal to 2t plus 4, where t is greater than or equal to 0 at the point t equals 1. Okay. So again, we first find our first derivative. Okay, so we know our dy dx is y prime of t over x prime of t. Uh-oh. Okay, so y prime of t is just 2. And x prime of t is 1/2 over t square root of t. So it will be t to the negative 1/2. So 1 over 2 square root of t, which becomes 2 over 1, times the reciprocal of that, which is 2 square root of t over 1. So it would be 4 square root of t. Okay. So now we find our second derivative. Okay, so we know our second derivative of y with respect to x is equal to the derivative with respect to t of your y prime of t. Oh, dy dx, sorry about that. Dy dx divided by dx dt. Okay, so that would be the derivative with respect to t of 4 square root of t divided by your dx dt, which, we'll put that in the next one. Okay, so the derivative of 4 square root of t, that would be, 2 over square root of t divided by your dx dt, which is, where is it? 1 over 2 square root of t, which would give us 2 over square root of t times, flip that, 2 square root of t over 1, where those cancel out, so we end up with 4. Okay. So in this case, our second derivative is 4 no matter what value of t you plug in. Any questions on that one?
Professor,
Yes.
in the question, what does t is greater than or equal to 0 at the point t equals 1 mean, like graphically? What would that look
Oh, that's just telling us that since it's a square root, it's going to be a
Oh.
real number. That's the only reason I added that one. And t equals 1, that's just, they just want to know the acceleration at 1. Okay, any other questions on this one? All right. Everybody's still right. Looks like everyone's done. Okay, so 2 more formulas and we're actually done. Area under a parametric curve. Okay, so when our x is equal to x of t, or function of t, y is a function of t, and x of t is differentiable, means the derivative actually exists. Then the area is equal to the integral from a to b of y of t times x prime of t with respect to t, where t is between a and b. Straighten it up. All right, so for example, find the area under the parametric curve defined by x of t equals 2t squared, y of t equals t to the third, and t is between 0 and 3. Okay, so we know that our y of t is equal to t to the third, and our x prime of t is equal to 4t. Okay, so our area will equal the integral from 0 to 3 of y of t times x prime of t with respect to t. So it'll be 4t to the fourth with respect to t. So if we integrate that, we end up with 4 times t to the fifth over 5. So it's just 4 over 5 t to the fifth from 0 to 3. So that would be 4 over 5 times 3 to the fifth minus 0 to the fifth, which will end up being 972 divided by 5. Right. Any questions on that one? All right. still writing. Oop, looks like everyone's done. Okay, so last but not least, the arc length of a parameter, or parametric curve. Okay, so again, let's say if we let x be a function of t, y is a function of t, and you have two values of t as your upper and lower integral limit. And also, x prime of t and y prime of t exist. Then your arc length is equal to the integral from t1 to t2, the square root of dx dt squared plus dy dt squared with respect to t. Oops. Okay, so this would be your formula here, but we're going to go a little bit further. Okay, so we know that your dy dx is equal to y prime of t over x prime of t, which means that your y prime of t is equal to dy dx times x prime of t. So what if we replace that in our formula? So from t1 to t2 times the square root of dx dt squared plus dy dx times dx dt. Squared with respect to t. Okay, so what if we multiply it by, it might have enough room on the other side. Square root of dx dt squared over the square root of dx dt squared. Okay, then that's going to give us s equals the integral from t1 to t2, the square root. I actually should have made that a little bit bigger. Move that over some. So we have the square root, that dx dt squared in the denominator, we can just combine that all together. So we have dx dt squared over dx dt squared plus dy dx times, oh, actually should have brought that up a little bit more. Dy dx times dx dt. Since both of those are squared, we can kind of distribute that one if we wanted to. We can make that squared and that squared divided by the square root of dx dt squared. And the numerator one, we can just bring that right out to the front. Okay, so the square root of dx dt is just dx dt, so we can just write that as x prime of t. Okay. So these two cancel out to just become 1. So that's x equals from t1 to t2, we'll take that x prime of t and put it back there. So that has the square root of 1. Those two cancel out. Of dy dx squared from x prime of t with respect to t. Okay, so we know that since we have x equals x of t, the derivative of x equals x prime of t with respect to x. Oh, with respect to t, sorry about that. So that means you can replace this with our dx. So we'll let t1 and t2 be some a values since we're going to use those, or a and b values. Times the square root of 1 plus dy dx squared with respect to x. So you can see how it fits into our old arc length formula. Oh, sorry about that.
Thank you.
Okay. You don't have to know this since you already know it from the past, but it's just kind of showing the connection between the two.
Is it easier to use this? Or you just proved it?
Oh no, this is just our arc length formula for when we just have our dy dx. That's the arc length of a curve. It's just the same formula we already knew. So if you see two different arc length problems on the test, it all depends on what they give you. So they give you parametric equations, you know you use this one. If they give you just a regular y function, you use that one.
So you were just showing the translation, those are two separate equations?
Oh yeah, you'd use those in two separate instances. This is for the parametric equation. So this is the one you're going to use here.
Okay. So is that just taking the derivative and squaring it for both of them?
Yep.
Okay.
Then you have the square root of that, and you integrate.
All right.
All right, so clean that up. And still leave that up for a few seconds.
You don't want to reset your timer.
Thank you. Actually, might as well do it now.